To introduce Professor David Patterson. Professor Patterson holds the bachelor's, master's, and PhD degrees from UCLA. He's an associate professor at the University of California, Berkeley, where he has served for the last 9 years. Professor Patterson has been the recipient of the Distinguished Teacher Award at the University of California and serves as a consultant to many computer-oriented companies. Today, Professor Patterson will discuss principles of reduced instruction set computers. And next Tuesday, he will discuss principles of reduced instruction set computers for exploratory programming environments. Professor Patterson?
All right. Thank you. I'm real happy to be here today to talk about some work that's been going on at Berkeley and Stanford and at IBM primarily for the last 5 or 6 years. These are ideas that we've been working on for a long time, and we're ready to move on to new things, but it seems to recently have taken on a significant commercial possibilities. So what I'm going to do today is describe the backgrounds, what we've bring you up to date, and talk a little bit about the commercial possibilities. And a week from now, talk about some of the more recent research. So what's on the transparency now is that I'm going to give you the overview of the background of how computers were built, or have been built, and these new ideas, the RISC philosophy, give you some examples and some numbers on execution time, and some conclusions and discussions. Let me say right now that this talk works best when there's interaction. And so I'd like to encourage you here in the studio and remote to try and use the phone number to call up and ask questions. It's a lot more fun with questions. The number is 415-857-8300. Apparently are 9 lines, so I think we can handle the phone calls. And if you're sitting out there with this really tough question and you don't worry about embarrassing me with tough questions. It's a lot more fun if you have to ask tough questions. But let me go ahead and get started now. My view of what happened is kind of modern computer architecture was defined in 1964 by the IBM family of computers, the System 360, and that was the first computer family. That is a range of machines that all run the same software that range in performance and cost. And that was kind of, IBM declared that computer architecture is not the same as implementation. And that allowed for some important marketing advantages. To allow this so-called family of computers, to allow a group of computers to all run the same software, that was principally achieved by microprogramming. The idea of microprogramming has been around since almost the very first computers. It really wasn't used very much until 1964. And the combination of the drive to have a variety of machines of cost and performance run the same software and some advances in technology allowed microprogramming to become very popular, starting with the 360 family. In fact, the advances in technology with semiconductor memory, particularly the read-only memories or ROMs, plus the core main memory became the standard way of designing computers, particularly mini-computers. This style of design was then rewarded by the academic research community. They felt that the push advantages should come through richer instruction sets. And these richer instruction sets, the advantages that were claimed, that they were going to simplify compilers, they're going to alleviate the so-called software crisis, that is, it's getting harder to build programs all the time and getting cheaper to build hardware, so why not have a richer instruction set to solve that problem. And basically there was a kind of a gut feeling that what was needed to be done was to improve architectural quality and everyone had their own definition of what architectural quality is. So while this was happening, of course, the implementation technology was increasing dramatically as predicted by Moore's law, doubling every year or two in the number of transistors you can get in the chip. So at the time, architects felt challenged. Damn, how am I going to keep up with this Moore's law? And one way they said, well, I'll build this large instruction set. That'll slow it down. That'll keep it busy for a while. And by the way, if it sounds like I said something funny, I intend to be funny, and so it's okay to laugh. And sometimes that covers when I make a mistake that's unintentionally funny, then you laugh as well. But what are some of the examples of that increasing complexity? The PDP-11, one of the most popular mini computers, the successor of that was the VAX-11, one of the more complicated computers that's been made. The IBM System 3 evolved into the System 38, which is a capability-oriented machine, fairly complicated machine. And the Intel 86, its follow-on machine was the Intel IAPX 432, again, a very complicated computer. All of these machines on the right are characterized by having a great deal of microcode on the order of, relative to the technology, on the order of 500,000 bits. Just in one example, the PDP-11, many of which were microprogrammed, had on the order of 50,000 bits. There's been a lot of members of the VAX family built, and they all have about 500,000 bits, about 10 times as many bits of microcode in this generation versus that generation, and similarly as we go across the list. So the questions arose is people decided to build complex instruction sets, but what was happening with these complex instructions? Well, in some cases, they were rarely used. Did it cost anything to have these complicated instruction sets? As long as something was microprogrammed, the line went, then it didn't cost very much to add a little bit more complexity, just a few more lines in a read-only memory. The other question that is brought up, and I think was brought to attention by the work that was done at Berkeley and Stanford and IBM, was in a rapidly changing technology, something that doubles the number of transistors every year or two. It may be dangerous to come up with a computer that takes many years to build, a long time to build. You have to be very good at predicting the future if you're designing a computer today that you want to sell in 1991 versus a computer that you're trying to sell in 2 years. So I wonder if in a rapidly changing technology you shouldn't look for simpler solutions so that you can take advantage of the rapid changes more easily. So what I put on the next slide are more or less what I call the design principles of these more complicated machines. So the acronym that some people use is this CISC to mean more complicated instruction sets. I think a better word is traditional instruction set design. But this typified that design. With the expanding memory technology, the technology that's being used to build semiconductor memories, that made it very easy to add more microcode. Read-only memories would have 1,000 bits in them 1 year, and a year or two later they'd have 4,000 bits. I guess 2 years later they'd have 4,000 bits. So you could increase the amount of microcode for a factor of 4 without even adding any more chips to the system. So it seemed like adding microcode, adding more microcode to the system was free, more or less. The other principle of this more traditional design was that microinstructions are faster than machine-level instructions. Thus, a way to get better performance for a piece of software is to move that software into microcode. And I have to say that's the research that I was doing, that my dissertation at UCLA, and in fact, one of my first consulting jobs after I was a professor at Berkeley was to consult here at Hewlett-Packard, and it was in this area of trying to get software, move it into microcode to try and make it run faster. The third design principle here is that speed is the same as program size, is that it was difficult to try and figure out what's a good architecture versus a good implementation of that architecture. So one thing you could try and do is say, how big was the program for that computer? And I'll give some examples on the next slide about what metrics were created to try and measure that. But there was the belief that if you could figure out a way to make the program take up less space in memory, then it was going to run faster. So you'll see people come up with a lot of machines, and some examples at the bottom of the slide, where why did it run faster? And the reason it ran faster was that the programs were smaller, and that's what they said. This final point of the traditional design is that registers were hard to compile for. A register-based machine was a bad idea because it made compilers more complicated and less reliable, and you shouldn't have them. And the style, how are you going to execute, deal with data and execute data? The way you're supposed to do that is either with a so-called memory-to-memory architecture, that is the operand state in memory, or the stack model, which was believed to be the compiler writer's ideal model dealing with a stack. So let me go ahead and bring some examples that typified that design. Okay, I think I'll just come right up here. So one of those was the IBM 370. This is one particular model, the 168. It was developed in 1973. The number of instructions is the next line. There's about 200 instructions. How big was the control store on this machine in 1973? It had 420,000 bits of microcode. The instruction size varied between 16 and 48 bits. One way to try and make smaller programs is to have variable size instructions so you can pack more, take as least amount of room as necessary. The 370, I believe, was built in ECL MSI technology. And this model of evaluation, it pretty well, the 370 covers all three. Either it's a memory to register style, that is, one operand's in memory and one operand's in register. You do an add instruction that takes something from memory, adds it to a register, and stores the result in the register. Or they also had the memory-memory style, both operands are in memory, and register-register. Pretty much IBM covered all the bits in the 370 architecture. This last line is the size of the cache. How big was the cache in this machine? It had about 64,000 bits of cache. Cache is a fast buffer memory, and we'll talk about the role of caches. But what's interesting is to note the relationship between this line, how much of microcode is the machine, and how big is the cache. And these machines, the factor of the microcode store to the cache size is on the other of 5 or 6 to 1. The VAX 11780, to follow on to the PDP-11 family, this is one of the probably the most popular 32-bit mini computer. It had about, built in 1978, had about 300 instructions, again having, like I said, about 500,000 bits of microcode. The VAX architecture, which was a new architecture in the 70s, the 370 is really very similar to the 360 architecture in the 60s. The VAX architecture extended the idea of variable length instructions dramatically. The smallest instruction in the VAX was 16 bits, and the longest was 456 bits. Why? The reason was that they attempted to, worrying about the code density, how big would the program? If they could make programs smaller, then they're supposed to go faster. This was built from TTL, and the style, again, it has all three styles of evaluation, and again, the size of the cache is pretty small relative to the size of the memory. This machine, the Dorado, is a machine that's not, of course, these are big commercial successes. The next two machines probably don't fit in that category. The Xerox Dorado, done about the same time frame, is a very expensive personal computer built for the research organization at Xerox Palo Alto Research Center, right up the hill from this TV studio. Had about 270 instructions, had about 130K bits of microcode. Its instructions were variable size, between 8 bits and 24 bits, so they really worked on the execution code size, and they used the stacked model of evaluation. And again, the cache is smaller than the microcode store. The IAPX 432, all of these have been big computers on the range of hundreds of thousands of dollars or millions of dollars. The IAPX 432 was a project at Intel to be the follow-on project to the 8086, the very successful 16-bit microprocessor. This was built from NMOS, so this was an attempt to be single chip. It actually ended up being 3 chips, having 200 or so instructions, and they really, and what was remarkable on this chip is that they had 64K bits of microcode on this small piece of silicon, and that microcode dominated that chip. And they took this variable instruction sets one step further by going to bit variable instructions. So this is actually, they had some instructions that were 6 bits, and the biggest instruction, at least the biggest one I could figure out, was 313 bits. And why did they go to bit variable? Again, try to make programs smaller. Why did they try to make programs smaller? Because according to the traditional design principles, that was going to lead to faster computers. And they used both the stack and the memory-to-memory model of evaluation, and because, I think, in my view, because they had dedicated so much of their silicon resources to this large microcode store, that prevented them from having any kind of buffering on the chip that would have helped their performance. So let me back up and say, so these were the design principles. More microcode is a good thing, doesn't cost very much. Let's move software to microcode. Both, in particular, the 432 typified that, moving operating system functions into microcode. Let's try and make programs smaller, and registers are dirty things, and don't ever use them. And this registers are dirty thing is best typified by, let's see, I've got the quote right here. Glenford Myers is a person who has written a lot of books about computer design. And so he said in 1977 or 78, One eyebrow should rise whenever a future architecture is developed with a register-oriented instruction set. So that was 1977 or 78. And so that was kind of the, like I said, there was this feeling of architectural quality that pervaded the community, and it was hard to quantify, but it was easy to have snappy remarks about that. So let me give you an example of the kind of the academic backup to this. And of course, the architecture that I'm going to talk to you about today does not follow that advice. So one of the ways of kind of getting academic respectability to these ideas was to have a metric, something that you could measure about a computer architecture, not about its implementation, not how fast does it run my programs, but how fast does this instruction set, how good is this instruction set? Try and quantify this gut feeling of quality. Well, was this line of arguments. The line of arguments was that a processor speed is limited by the memory bandwidth. That must be true. If you have a 1-bit path between your CPU and memory, it's going to take a long time to get that amount of information. So given that must be true at some level, is it a first-order effect or a second-order or a third-order effect, it's hard to say. Let's try and reduce memory traffic. Let's try and measure that. So memory traffic is composed of all of the instructions you execute. That's the I measure, the total size of the executed instructions, and plus the data measure, the total size of the data that you have to fetch. And so M, which is the sum of these two. So let's go through an example and show you a few different architectures. And people use this metric. This metric was developed and used to decide which was the best architecture. In fact, there was a project that was developed and funded by the military that came up with these metrics to try to decide what is the best computer architecture for military so they could have one standard. And this was used in that evaluation. So the example I'm going to do is A gets B plus C. And let me show you how this metric works. All right. So what the model on the left, remember I said there were 3 memory models. There's register-to-register model, memory-to-register, and memory-to-memory. This model on the left is a 4 instruction sequence to do this one. B plus C goes to A. So in a register-register architecture, you have to get things into the registers, so you have to do loads to get them there. So here are 2 loads to load these 2 registers. Here's an add that deals with all 3 registers, and here's the store. So using the metric that we saw, what's the total size of the instructions, total size of the data, and to get this M figure. For this, it's the total size of instructions. I assumed that this was 8 bits for the opcode, 4 bits for the register specifier, and I think 16 bits for the addresses. If I add that all up, the total size of the instruction is 104 bits. The total size of the data, there's 3 operands, read B, read C, store into A. That's 96 bits. So the magic number M for this architecture was 200. Here's a memory-to-register style of machine where it's dealing with a single accumulator. So it loads this into B, it adds that from C and stores it into A, and that ends up, the magic number for that is 168. And this bottom one is the memory-to-memory style register. It says, do an add, and the operands are located in memory, and store the result back in memory. So this one reduced this down to 152. Back up a little bit. So what people did in that study, trying to decide a standard computer family, is they use these metrics to decide that this one isn't any good, this one isn't any good, and this one's the one to use, and that influenced the design of machines. And that's why I think machines like the VAX went to the memory style, because when Glenn Myers made that comment about machines that use registers in the future have to be, we should all raise our eyebrows when we see that. He was saying that the memory architecture is the clear winner, and only a fool would design a register-oriented machine. So what happened to those machines of the 70s? What happened to that design style? Well, one of the first things that happened was that microcode errors changed the control store from read-only memory to random access memory. And in fact, I took a leave of absence to visit DEC in the fall of '79, and the reason that I was there was because DEC was frankly having problems in building this VAX architecture, and that there were a fair number of mistakes. The 780 had, which is one of members of the family of the VAX 11, has a lot of read-only memory and some random access memory to patch errors, and they were finding lots of mistakes in the machine. And that's where my research was trying to remove mistakes from microcode. Well, what happened, manufacturers would build a machine because read-only memory is less expensive than random access memory, and so they build the machines because the hardware cost is less, and then they get out in the field and they have these microcode errors. They have microcode errors because the poor microprogrammer had to get 500,000 bits, 500,000 combinations combinations of zeros and ones to fill up 500,000 bits exactly right, and if he didn't, he got in trouble. And so people tried that, and at the same time, if the machine was slow, if the microprogramming wasn't fast, he got in trouble too, so that was a tough situation. They solved that on almost all machines by going to random access memory instead of read-only memory. So that happened. That made microcoded machines a little bit more expensive, but it wasn't that big a deal. The other thing that happened, because of advancing technology, as predicted by Moore's law, is for the mini computers and most computers, is the main memory was no longer this core memory, the fairly slow magnetic memory. Instead, it was the faster semiconductor memory. The other thing that happened is caches were invented. These are these buffers that were invented that allow you, that use a probabilistic argument. That is, that if a program's in a particular area, it's more likely to be able to access something that's used recently. So if it's touching something near location 100, chances are it's going to touch something near location 100 again, rather than randomly walking around memory. And so what happened? So what happened was main memory became much faster. So in the traditional architectures, the speed of the control memory, the microcode control memory speed. In the traditional architectures, it was 10 to 1. That is, the control memory was 10 times as fast as the main memory access, because this was core memory, or this was semiconductor memory. But the changes that happened in the machines in the 70s is that caches came along. This is 10 times faster. Okay. So with the addition of caches, just the concept that you can build a very small amount of high-speed memory, plus the fact that the semiconductor memories behind those caches were much faster semiconductor, this ratio dropped drastically on the orders of maybe closer to 2 to 1. The other thing that was interesting that happened is what were they building these control memories from? They were building them from random access memories. What kind of random access memories was those? Because the speed of a microinstruction controls the speed of a computer, you wanted those to be fast as possible. And in fact, what was happening is the very same chips that were used to build this control memory were the chips that were used to build the cache. And although people widely agreed that caches were important for performance and they should be big, because of, in my view, historical reasons, tradition, the amount of this RAM that was in control memory is usually 5 to 6 times the amount of in cache. The other thing that was happening to these machines of the 70s was that the compiler writers didn't necessarily agree with the architect's vision of adding more complex instructions to make their life better. Compiler writers would tend to find difficulty of using these more complicated instructions, had a hard time using it. So what the compiler writer would do when faced with, he has to make a program that is fairly fast, a compiler, and doesn't make mistakes, and he sees these complicated instructions and have to go through a very difficult case analysis, the compiler writer would frequently drop out the features of the architecture. So something strange was going on. People were working very hard to build machines with a lot of sophisticated, very rich instruction set. These machines are getting more difficult to build because the microcode may not have been more expensive, but it took a lot more design time to get it right. And we ended up with machines that have a lot more of this important fast RAM memory in the instruction set for the microcode than we did in the caches. So that's about when that's when people got involved with these crazy ideas I'm going to talk about next. So one way to say is what happened, there's what's called a semantic gap. That is, with a low-level instruction set like people used to use in the 50s, compared to these sophisticated instruction sets like the 432 or the VAX, that closed the gap between what people would program in high-level languages and what the machine would execute. And so you could say what had happened in these 70s is they replaced this semantic gap by a performance gap, is that machines weren't running as fast as people thought they should. The other thing that's strange that was happening is that because of the cache was built on the same chips as the microcode memory, we ended up with a microcode memory. We're trying to fetch instructions at the same speed as we're executing microinstructions. So more or less what happened was this next hypothesis. How about use optimizing compilers to generate instructions as simple as microinstructions and making the cycle time as fast as technology allows? What would happen if that happened? Well, this gave rise to the reduced instruction set computers. That is, not very many instructions compared to traditional machines, but in particular, the emphasis of that name should be the reduced instructions, the attempt to make them as simple as microinstructions. So that rose to the acronym Reduced Instruction Set Computer. Carl Sagan, a colleague at Berkeley, came up with that terminology, and it's caught on. And we meant at the time when we came up with this acronym, when we were doing this work, that it was a pun because we weren't sure what was going to happen when we tried this. It was risky business, and that's why we tried to reflect that in the name, the acronym. And so in our own fashion of trying to get across the idea of well, how could something simpler be faster? Why wouldn't something more complicated be better? Then we tried to illustrate that. And if you talk to people about RISC ideas, they get very upset. It's a religious, emotional reaction on the subject, although many people come around. And I was wondering why that was true, and I wouldn't be surprised if it was things like this that got people emotionally involved. But more or less, this is, for those of you who aren't car buffs, this is a 59 Caddy, and this is supposed to be a Porsche. I don't know if that was the best example, but at the time, when our research was funded by DARPA, we had a hard time picking a Japanese automobile here. Seemed to set the wrong tone, but maybe a Japanese automobile doesn't have any tail fins. It's light, fuel efficient, could still end up with being a better automobile than something that people had been building for a long time. Okay, so if I gave you the principles for the design of a complex instruction set computer or a traditional machine, what were the guidelines that followed these RISC guidelines? What were the principles that we tried to follow in what we were doing? And sometimes we followed them and sometimes we didn't, but this was what we tried to do. Keep it simple unless there's a very good reason not to. I've heard that said lots of different times. Another good way to say it is use your intelligence to simplify the solution. The 10% rule means generally what architects do is they try and optimize an architecture. They try and add things to it. They're going to reduce the number of cycles it takes to get the work done. Unfortunately, and I think in part because IBM announced that the architecture is not the same as implementation, is they tended to forget about how long one of these cycles would take. So the 10% rule is if you come up with a wonderful architectural idea that saves 10% in cycles, saves 10% of the cycles it takes to execute a program, but it increases the cycle time by 10%. Cycle time by 10%, you haven't made any headway. The programs take the same a long time to execute because you multiply the number of cycles by the cycle time to figure out how long it takes to do work. So we made a real emphasis of trying to keep things simple, and a way you can build faster computers is to shrink the cycle time, and that idea kind of wasn't paid a lot of attention to for a while. The other design principle is microcode is not faster than simple instructions, especially for a cache-based execution. As my understanding is the lecture after this one is going to be by Harold Stone, who's now at IBM. Talk is going to be about cache memories, and I think that'll be a nice tie-in to this lecture. But given that caches work well and that we can build caches from the same chips as we can build microcode, we can get that high performance. The other thing that typified the traditional designs is somehow microcode was magic, and I probably, with my research, helped what I was doing after my PhD. I was helping support that idea. Well, we'll just move this software into microcode and everything will be great. But it's not magic. In fact, it's not even that great. It's a lot harder to change stuff that's been moved into microcode. And what's the difference about a runtime library versus keeping something in, especially if you had to put the microcode in ROM? A runtime library for a RISC machine has the advantages of its software. It's changeable. You don't have to fix it before the machine's been shipped. You can change it any time during its lifetime. So this runtime library versus ROM and microcode it's hard to see if it's running, if the cycles are as fast, why not keep it in the runtime library? This is one of the areas where people say RISC machines just offload that function that from the hardware people into software, and I think I agree with that. But writing a cyclic redundancy check routine like there is in the VAX instruction makes more sense as a runtime library routine rather than something that has to be built into every VAX that's ever going to be made. And the last two principles of design are stick to a simple decoding size. The RISC machines uniformly ignore the advice about trying to make programs smaller so that they run faster, and they reward simple decoding so that they can get better pipeline execution. And we think that's a lot more important than program size. And the last thing is try and use compilers to simplify, keep the operands and registers so that they can be reused, and deal with loads and stores to memory. That also simplifies virtual memory implementation. So let me show you some of these machines that are the three best examples, I think, of the RISC. First one is the IBM 801 project. This is a real interesting project. They actually had a machine working in 1979. It was built in ECL. I have brought with an in fact, let me back up a bit. I think this article's been handed out, but if not, it's the, I'll back all the way up. This is the January 1985 edition from CACM, and it's about computer architecture. And here's a picture of the IBM 801. First picture I'd never seen this machine, so I was real interested to see the picture. This machine is, let me get closer. This machine was built out of ECL technology. The work that was done at IBM was done in the 70s. It was, this machine had a cycle time of 66 nanoseconds. And like I said, it was up and running in 1979. Unfortunately for everybody, the people involved in the project and for those of us in the research community, IBM was unable to talk about the 801. In fact, the first paper was published in 1982, I think in part because of a conference that was organized by a former Berkeley student. And he tried to twist IBM's arm to say that they need to publish to get credit for the work that they'd done, and that helped let them be published. But IBM, as a corporation, I guess, or for whatever reasons, decided to sit tight on this technology, and there were a lot of rumors about the technology, but didn't know exactly what they were doing, and some of the articles that were in the popular magazines weren't very helpful. But it was a real interesting project, but there it was. They had a RISC machine working in 1979, and this work was led by John Koch and had the involvement of a lot of people at Hewlett-Packard. But I think John Koch, if you had to pick one name, that's the name you would pick. The work that came after that for the RISC machine, this 801, is the work in VLSI done at Berkeley. This is a photograph of RISC-II. We had a RISC-I that was a VLSI implementation that was done in 1981, and RISC-II in about 1982. And this is, instead of being built out of boards worth of cards, this is built out of custom NMOS. And we'll come back to this design later. This section, this large black hole here, is the register file. So this is a register-intensive design. This was a very nice design done by two students, Robert Shearburn and Manolis Katavenis. Robert Shearburn's now on the faculty at RPI in New York, and Manolis Katavenis is on the faculty here at Stanford. Shortly, not too much longer after we started our project at Berkeley, there was a project at Stanford. This project is called the MIPS project, and this is their first machine. It was something like 6 months or a year after the Berkeley project. This is, again, a custom NMOS implementation, and when I get to the end and talk about commercial possibilities, this chip will play another role. So let me go back to those machines, the characteristics there. So compared to the previous slide, like I said, the IBM 801 was done in 1979, about 120 instructions. Here are the years for the MIPS and the RISC machines. Fewer instructions there were in the 801, but like I said, the main thing about the acronym is the simplicity of instructions. None of them used any control star. All of the instructions were the same size, and the technology, these were two chip designs, custom chip, and this was ECL. And all of them took the register style of execution. If we contrast that with these more complicated examples, let me just come up here. You can see the numbers of instructions are much higher. The variable instruction size is the big differences, and the variety of execution models. Okay, so those are the examples of the machines. So let me go over some of those design principles we talked about earlier. One of the design principles is to try and keep things to be register oriented operation. So let's show an example of using registers using these metrics that were done before. Here's the old metric that I showed you before, and the winner was this one. The winner was the memory architecture because it only needed, I think it says 152 bits. So rather than just, this was A gets B plus C, and that was what this one was. Now let's look at it again, a little bit bigger program. Okay, so let's look at this program. We have a sequence of 3 statements: A gets B plus C, B gets A plus C, and D gets D minus B. If we go over and look in this, here's a register architecture where the operands are all located in memory. And if you do all these loads and stores, the magic number that you end up with is 420. Now, if we compare that to the winner from the last time, the memory architecture, the answer is 456. So that's surprising. What happened from before that made the register architecture good compared to where we're supposed to raise our eyebrows at this one compared to this one? And the problem with the memory-to-memory architecture, the reason it was bigger, is there's no opportunity to reuse operands. The operands have to be refetched from memory every time you need the longer addresses. If you look back here, you can see that we use C twice and we use B twice. And Marty Hopkins, who's one of the compiler experts who works on the 801, believes that is the principal advantage of this style of architecture, the fact that you can reuse operands. So that by looking at a sequence of instructions, the reuse of operands allows you to have a winning advantage compared to the memory-to-memory architecture if you believe this metric is important. Now, if you can have real good compiler technology and you can keep all of these operands in registers, then it looks dramatically better by this metric. The total memory size is 60 because the operands are in registers compared to 456. So our idea then is to try and have a register style machine with loads and stores to access memory, and what the goal of all RISC machines is to keep these operands in registers. And what we're going to talk about next is 2 ways to do that. One way to do that is with really good compiler technology, and another way to do that is with a trick called register windows. I guess that's going to come in a couple slides. Okay, so keep that in mind. We'll come back to that. How about the instruction formats? Whereas the 432 had 6-bit instructions and 313-bit instructions. All the instructions for these machines are all 32 bits. This is the format for RISC-I and RISC-II. Here's the opcode, which is 7 bits. This is setting the condition codes, which is kind of like 1 bit of the opcode. The destination field, the rich destination, is this is 5 bits. This source 1 is 5 bits. The immediate field here, which is to assign whether or not this is immediate or the register field, this was 1 bit, and this is 12, which has it. I think that all adds up. Every single operand takes the same format. So what? Why does that matter? What it matters is when you're trying to execute and decode and build a pipeline computer. So here's the format for RISC-I for this sequence. A gets B plus C, A gets A plus 1, D gets D minus B. So you can see for the RISC style, every single opcode and the destination and sources are all in the same location. What that allows us to do is reduce the cycle out of the pipeline. So that makes the decoding time much simpler at the cost of having wider instructions and bigger programs. If you compare that to the VAX, the border lines, so here's one instruction right here. The second instruction goes from here to here. And the third instruction wraps around. So this is a 32-bit wide port that we're looking at. And for the RISC instructions, every single one comes out in the same location, the same spot. We don't have to look at the opcode to decide what the operands are. We can immediately begin decoding starting reading the registers as soon as this instruction arrives. The VAX, you have to do some extra work to figure out where the operands are specified. What the VAX does is this. Here's Here, assuming the operands and registers, we can use this style of instruction. For this A gets A plus 1, this is an example where architects optimize. It says the special opcode that says add 1 to an operand, and that only takes 2 8-bit quantities to specify adding 1 to it. Whereas the RISC machine takes the full size. We specify the source, we specify its immediate operand, you add 1, and the destination. This is a real good example of architects doing optimizations to try and reduce code size. It's not going to particularly run any faster, but unless you believe that smaller programs leads to faster programs. It has the disadvantage of requiring the alignment of instructions that could be up to 456 bits, so I think that was on the order of 45 or so bytes, the longest instruction. So trying to do some pre-alignment of operands and locations to get that same benefits is more difficult for the VAX. And what's shown here in the bottom is the 432. The 432 has bit variable instruction sets with the goal of getting smaller programs, and so when you look at it 32 bits at a time, it's real hard. So here's one instruction. And here's the next one goes around and wraps over here, and the third one is down at the bottom. The 432 had an interesting architecture. As part of the opcode was at the top, and part of it was at the front, and part of it was at the end, making it more difficult to do fast decoding of instructions. Okay. Now, I said the operands and the RISC design principles, you're supposed to live up to the name of reduced instruction set. That is, we have single cycle execution about as fast as a microinstruction. There's no microcode in the machine, it's hardwired control, and the only addressing modes are indexed in PC relative addressing. And this is the list of instructions that were in the RISC instruction set. The Berkeley RISC instruction set. There's just not that many things there. I guess they're on the order of 30 or so of them. And the one other thing that the 801, the RISC at Berkeley, and the Stanford MIPS shared was trying to reduce the pipeline penalty. If you take a close-up, here's the sequential style of execution where you go through the 5 traditional stages of instruction execution: instructions fetch, instruction decode, operand fetch, operand execution, operand store. Here's 3 instructions going through this. The pipeline model is trying to do one piece at a time and make progress that way. So on the average, you get an instruction done every single cycle. The difficulties arise is when there's some dependencies between these instruction sequences. For example, if this instruction is a branch, then we don't want to, we have to wait to where we branch to and then start instruction again. That causes so-called bubbles in the pipeline. So what the RISC machines do is they redefine how branches work. They have the so-called delayed branch. So rather, conceptually, first of all, they also try and keep the pipeline short so there's not such long gaps. But here's a jump instruction where normally you would stick in a non-operating instruction so that you'd have time to branch to this following instruction. This looks like it wastes the cycle. What we try and use compilers to do is to stick in some instruction to follow the jump so that we can do something useful in this dead time. Okay, so the idea has to do with pipelining. You want to do something useful in this time, and we just redefine how jumps work, take one extra cycle. Let me show that with this figure. So here's the way branches normally work in this sequence. This is on page 18 of the paper. Normal sequence is it comes down here, you do the jump, then you branch around to location 105. You just do a jump like this. Okay, so with what we call delayed branch or the delayed jump, it's now redefined. And put these two next to each other. The jump is going to take an extra cycle, right? So you'd have to stick a no-op there, and rather than jumping to 105, you jump one more down. So the jump, this is the jump instruction, then you execute this, and then it comes down. So the jump actually takes effect here, thus the name delayed jump. Well, that seemed like a silly idea. It just makes programs longer, and you still waste a cycle. Well, that's where we try and use compiler technology to replace this with something useful. Well, it turns out this add instruction could be executed in this slot and get the same effect. So by switching the order of these two, we can get rid of the no-op and then go load, jump, add to a delay, and it comes down to this location. Okay, so let me back up a little bit and show you those. So here's the optimized delayed branch, normal branch. What does that take in terms of hardware to provide that time of optimization? Very little. It takes an extra program counter or two, but not much in terms of hardware to get this delayed branch. Traditional machines, optimizations of branch prediction can be very elaborate hardware mechanisms that are very difficult to build and can actually slow the cycle time of the machine. This RISC idea is, again, to use something very simple, try and get software to take it to provide that. How well does it work? How frequently can we optimize? Well, if you the studies at IBM and at the studies at Stanford is that a whole lot of the time, well, there's say 10% of the instructions are unconditional branches, and 10% are conditional. That's reasonable, a mix of instructions. The unconditional branches, you get for practically all of them, 90 to 100%. So only 1% of the time is wasted, whereas in traditional machines, that would be a wasted cycle. And on the conditional branches, say you can get half of those. The results are even better with the more optimizing compilers at Stanford and at IBM. They get a higher fraction of that. But rather than wasting 20% of the time with straightforward technology, you could gain as much as 14% in performance just from that one trick. And one of the interesting things about noticing of the difficulties of branches that follow, and this was done by John Hennessy, we did all these studies on elaborate metrics of how to get programs getting higher performance by fetching fewer instructions. Well, that's not really taking into account is the fact that there's generally a buffer to be able to fetch these instructions on, and that the fact that this buffer gets loaded up on machines like the VAX, and the access is really going to the buffer to memory, and so there really is traffic going on even when there's a jump. The things that trail in the buffer won't get executed, but they are fetched from memory. So about 1 in 4 instructions actually change the program counter, according to studies at DEC. So it's reasonable to expect that there's about 20% more bytes fetched from memory and loaded into this buffer that would actually reflect it in the architecture metrics. Okay. I think I've been talking for a long time without interruption, so let me talk about one more idea and then stop and handle some questions. This is basically the floor plan for the RISC-I machine. When we had done this design, it was our first chip that we'd done at Berkeley, we had laid out all of the register file and all of these pieces, and we hadn't yet done control. We invited a designer from Intel to come, and we said, well, what do you think? And he says, well, you're in big trouble. That's also already a very big chip, and you haven't done your control yet. And he says, but we have a real simple machine. He says, yeah, I've heard that before. Control is usually more than half of the chip, and in fact, that's true. Machines like the 68000, the 432, on the order of 40 or 50% of the whole chip is the control area. Well, fortunately, we had students go ahead and use the PLA tools to produce the control that we need for the chip. Unfortunately, it was a very small PLA. That's the piece right here. This is PLA here. PLA here is the basic control. If I go back in, the designers of RISC-II, which using the same technology built an even smaller chip, decided that was far too much area for control. So let's see if I can. So yeah, the control area for RISC-II is right here. It's this piece right here. I think that's just about it. They didn't even use a PLA because that would be too big. They built themselves a little latch. So the control area is drastically reduced. What we say is by reducing the control area and trying to get simple performance, that leaves us more resources to do things. And what we did on the RISC project was to build a larger register file, although you could clearly do many other things in that. By making the machine simpler, in the university, it has to be important for us to reduce our design effort. Now, it's dangerous to compare commercial and industrial design efforts, but well, it took us much less time to build it. It seems to make sense that if it's a lot simpler machine, you're going to have a lot less problems in the design, and as I'll mention later on in the development or actually trying to produce lots of copies and have people use them. Okay, so I've been talking for a while. How about some questions, either from out there in all over America at 415-857-8300 or locally in the studio. All right. Go ahead. Yeah, I think they want you to push the button there.
In that metric you mentioned, it talked about the time taken to fetch the operands from memory, but it didn't take into account the execution time of the instruction, which would presumably be faster if the operands were in the registers.
Yeah, let's see. The metric that was proposed, actually, this was done in Carnegie Mellon. They had 3 pieces of that. It was program size, the amount of data traffic that M measures, but the actual size of the program. The third piece is what they called register-to-register operations, or register transfers or something. This is a very vague notion of somehow trying to capture the amount of cycles involved in executing a program in some architecture. This was very hard to do because they had to come up with a model of execution for all of these architectures because it was architecture, not implementation. And that model of register access didn't end up being popular because no one could figure out how to account for it. Although in the study that they did for the computer family architecture, they did try and include that into account. So what ended up happening is just that measure of memory traffic and program size was what got picked up and reused. And so when architects would sit around and try and design new instructions or design a new architecture, they end up concentrating on that memory traffic, in particular program size. It was very popular at that time for people to look at sequences of instructions, thousands of instructions, and look to see if there was any pair or triple of instructions that collapse into a single instruction, thus making a better machine. It'd have fewer bits it would take, and therefore, and the belief is if you collapse 3 simple instructions to one complicated one, it would have to go faster too. So they didn't, it ended up not reflecting kind of the work that had to go inside the CPU, and thus, you know, ended up with some pretty exotic instruction formats. A bit variable instruction format is a very exotic thing to do, but that was kind of the sign of the times. Okay. Are there any other questions? I can wait, you know, a long time. Let's see, do I have any other questions about me? So from the things I've covered so far, well, how did we go about designing our instruction set? I'll ask myself that question. What we decided to do was to look at high-level language programs and see where they spent their time. And what we found is when we looked at high-level language programs, because that's what the programs we thought were important, we thought that what we do is see where all their time was spent. I think I may have a slide on that. But what we found is that very simple instructions dominated that time. Let's see if I've got that. Right, here's this next slide. Messed up my order here. Okay, but we find, so if you looked at the frequency of occurrence here, the assignment statement dominated that time, and then there was the if statement, the call, a few other statements across the top, but the assignment statement dominated that time. What we did is that if we change this though, we looked at what the execution time was for these pieces, because assignment's pretty simple, and if statement and so on, we found that the call statement dominated, that the call statement would come up to the very top of the list of things that would dominate execution time. And so we really concentrated our architecture for trying to execute call statements very fast. And in fact, that's what this next slide is trying to recognize, is that if we weight that, in terms of just frequency of instructions, if we weight it and we go across to the weighted instructions, we see that the call instruction becomes one of the most expensive instructions in the machine, followed by the loops. That's what I'll talk about next. There seems to be a phone call from Bob from Phoenix on line 0. Okay, Bob, you're on.
I have a question. You know, historically, registers were an expensive item, and so people tended to have very few of them. Now that hardware is fairly cheap. Have you done any studies on an optimal number of registers for a RISC system where, you reach some point where adding more registers
can a compiler use effectively? The other side of the coin is when you do a procedure call, you have to save some of those registers away or all those registers away. So if you add too many registers, they could slow down your procedure call. So I'd say the common wisdom from the compiler designers is that probably 32 is the most popular number, 32 registers. The others, and there are some people who think 16 registers are enough. John Hennessy's design of the MIPS computer had 16 registers. Depending on how good the compilers are, 16 can do, or 32. What you'll see next after the break is what we did. We have essentially 32 registers at a time because we had real simple compiler technology. And we have a trick to make procedures still go fast. But I think this is the common wisdom. What's interesting about that is the very popular microprocessors, 32-bit microprocessors today, don't do so well there. The 68,000 class machines, 68,000 10s and 20s, end up having two types of registers, 8 data registers and 8 address registers. And there are only some operations work in each of these. That was just an attempt to try and pack instructions into 16-bit words, and unfortunately, that wasn't, so they had to have separate types of registers rather than having a uniform 16 registers. That makes the 68,000 not quite as attractive. The 16032 and 32032 from National, these two machines, have the same architecture, and they have 8 registers without any restrictions on it. The VAX machine had 16 registers, but unfortunately there's a lot of restrictions on these registers, so that there's 3 registers are used. I guess one of them is the PC, one of them is the stack pointer, one of them is the frame pointer. And this cuts down the number of registers to more like 13. So one of the things you'll see in these RISC-style machines is that they go to a larger number of registers, making it easier for compilers to use those registers, and therefore keeping operands and registers more frequently. But then the question is, what's the consequence on procedure calls and returns? Do you have to save all these registers away? So I think if you talk to compiler writers, they'd pick one of these two numbers, and if those are the numbers they'd pick, then they wouldn't be too happy with the machines that are commonly available. Okay, looks like we got another phone call. Mike from Burlington. Okay, Mike, you're on the air.
Yeah, hi. I wonder if you could talk to the interrupt structure was like on the RISC-I and II, especially as concerning levels, priorities, impact on the pipeline, especially as to the size of the control logic.
Okay, that's a good question. Why don't you hang on and see if I come up with a good answer. My particular opinion is that interrupts are not a real hard thing to understand. I can buy a chip that's called a priority interrupt decoder. And what we did was just, here's a RISC chip. It just has one interrupt line, and our plan was you stick a priority interrupt decoder to there. Since that time, I have found people who've asked that question are absolutely unconvinced with that concept. So the machines that we're doing right now have the SOAR machine, which I'll talk about next week, and the other ones. We just decided to go ahead and put all the interrupt lines in. That's true. One of the differences between the 68,000 machines and our machines is they do have priority interrupts built into the chip, and we don't have that logic there. So thus, it's a little bit. That's a great way to build computers, is not have to have the hardware. Let's see. In terms of the interrupt structure, so we relied on external hardware to prioritize the interrupts on RISC-I. On RISC-II, we had essentially four classes of interrupts. The two of them dedicated to window overflow and underflow, which I'll talk about next. And underflow, and then 2 external ones. Like I said, I think, in my view, is that the priority, the interrupt mechanism uses up pins and not very much else on the chip. A little bit extra hardware for masking the interrupts, and the interrupts we allowed interrupts, so I don't think the pipeline, we still have to have, the pipeline had to work on interrupts, and we had to make them work on page faults. Loads and stores could be restartable. but we didn't build a priority interdecoder. Did that answer your question? Or did you have a follow-on? Are you still there?
It just seems that going from RISC-I to RISC-II, that if you did indeed reduce the amount of control logic, that you came out with a simpler control with more effect in it.
Right. What RISC-I was kind of the blitzkrieg model of getting a chip out the door. These students were taking 2 quarter courses and they had to graduate. So RISC-I was done in, the course started in January, and in June we submitted the chips and got it out the door. RISC-II was done in a more leisurely fashion by a smaller group of people who wanted to make a very elegant design, and that is a real nice chip. And the things I didn't say about RISC-II, let me put it up again. I like looking at it, but this actually has about 75% more registers, and the control area is smaller, even though it's the very same, and it's about, the chip itself is on the order of a third smaller than the former RISC-I. So it was a real nice design. It was an example of, we had a person who knows computer science and a designer who knew silicon very well, and they were able to take their time and do a very elegant design, and that was an advantage over RISC-I. Okay, thanks a lot.
Thank you.
And let's see, I think we have somebody, Harmon from Phoenix. Whoa, Harmon?
Yes, David. I have a question. You, in your paper, VLSI RISC, and I guess September 1982, you used this term that says complex instructions found in CISC machines are subroutines in RISCs. Then today you used this term runtime library. I wanted to get some more information on that. Can you elaborate on that?
Okay, I think your question was about, I said runtime library versus subroutines. Okay.
Yeah, I couldn't figure out what, I couldn't agree.
What do I mean?
Not that agree. Couldn't figure out how you using these subroutines in RISC to replace them in CISCs.
Okay. I think I got that one. So I said a runtime library today, and before I said subroutines. Okay. Yeah. Well, what I mean by runtime library is just that generally there's the compiler's view of the world, like the C compiler, and the compiler takes programs and produces object code. Well, it turns out that the other thing that it does is you have to link the object code with some built-in routines like sine and cosine. So this is what I mean by runtime library. Whoops. Sine, that's probably sine and cosine are examples. Mathematics library. Also, all the routines to do the input-output, the printing routines, are linked in a runtime library. So that's all compilers and all systems have the concept of a runtime library in compilers. But we said, well, what about some of these complicated instructions like a cyclic redundancy check? Cyclic redundancy check is actually, which goes and counts the number of bits and is used to calculate error code. This a fairly elaborate routine is actually an instruction on the VAX. There's an opcode dedicated to it and a lot of microcode dedicated to it. What will we do on a RISC machine? Well, I meant it to be a subroutine, or it'd be in the runtime library. So when you want to do cyclic redundancy check on a RISC machine, you'd also have to have the CRC instruction or CRC routine in this runtime library. Now, why I think this is a good idea is that in a family of computers, every single one of these is supposed to have a CRC instruction executed in it, dedicated to microcode, no matter whether it needs it or not. And if there's a mistake there, it's going to cost money to fix it. The runtime library is all done in software, and that's something that you can change over time. Every time there's a new release of the operating system, it fixes bugs in the operating systems. It can also fix bugs or have new versions of the cyclic redundancy check. An advantage of this style of machine is if there's new ideas that come along, like better ways to calculate sine and cosine, all software is just a good idea. You can change the software and the machines can take advantage of it. If you build it into the hardware, you can't take advantage of that machine. So when I said complex instructions are either subroutines until I use runtime library, that's meant logically that subroutine would be included in the runtime library and be called in by the compiler. Did that get your question?
Yes, sure did. This also includes the floating points,
Yeah.
subroutines? Or
Yeah, floating point, I'll see how much time I have next time. But yeah, because there's no multiply, it's one cycle instruction. So multiply and floating point and all those things would have to be runtime library routines on a simple computer. And so that takes a little bit more space, where it would have been microcode space in a complex machine.
what about time-wise? Because if
Yeah. Well, what the time-wise is, the argument is, if it's just a simple algorithm, there's nothing fancy, no fancy hardware, then if you believe that RISC machines execute instructions as fast as micro-instructions, then we argue that it should be comparable in performance. Now, that turns out to be, for floating point, that's not the case. RISC machines have pretty poor performance because the complex machines put special extra hardware in so the micro-instructions are more effective, or in particular, they put in a whole board of floating point hardware to make it run faster. So I'll try and talk about that next week, about floating point performance. For right now, if you're interested in floating point, all of the results that have been published so far say that, well, RISC machine's a bad idea, unless you think Seymour Cray is a designer of RISC machines, and then you'd buy one from Seymour Cray.
thank you.
How about Stephen from Livermore? On line 0, Stephen?
Yes, my question is, since you're doing a large number of registers, the register-to-register architecture, what are the implications in a multiple CPU environment?
What, okay, I think I didn't. What do I think about multiple CPU environments with this? Is that what your question
Yeah.
is?
Since you can have a large number of registers, and instead of a memory-to-memory architecture, it seems it would be more difficult to implement a multiple CPU computer system.
Okay, let's see if I can do this right. I'd like to be prepared here. So, just as long as I have a national audience. Let's see. Well, so this is what we've done, and this is what I'll talk about next week. This is the project we're working on right now. This is a poster we used to try and get Berkeley students to take our courses and get involved. But the project we're working on right now is a multiprocessor. And so what we're real interested in, on the order of 6 to 12 processors. We're taking you can think of what we're doing as a step-by-step approach, looking these two machines, RISC-I and RISC-II, kind of looking at the instruction set. This one's looking at exploratory programming environment, in particular garbage collection issues, and at that level. This one, the SPUR project, we're going to try and tackle multiprocessors. As far as we can tell, there's very little about an instruction set design or register orientation that has to do with multiprocessors. Multiprocessors has to do with the sharing of information in memory, or perhaps you're going to use a message-oriented. I guess if you're going to use a message-oriented way of sharing, you might want to do that in instruction set. But we believe RISC machines are nice, fast computers, and if you're going to build a multiprocessor, it makes a lot more sense to build out of fast computers than it does to build out of slow computers. And so we're going to try and work on that, but that's hand-waving right now as opposed to any proof. Our guess is that RISC machines will be fine to use in a multiprocessor system, but that's work that we're going to do, not work that we've done. Okay, okay, good. That was a nice group of questions. Let me go. I'm ready to go on for a little more and try and talk some more. So there are a lot of these things that we had, a lot of similarities in RISC machines. But because there are 3 different projects distributed all over the country with different goals and different resources, they ended up having some variations too, about 4 of them, in fact. So one of them is, how do you keep... RISC machines make sense when your operands are in registers. And they don't make a lot of sense when the operands aren't in registers. A register-register architecture with everything in memory isn't going to run too well. So the scheme that's being used at IBM, a major difference between IBM and Stanford versus Berkeley is the reliance on compiler technology. The key thing of compiler technology that I can just quickly illustrate that's being done was done at IBM is the so-called graph coloring scheme. This graph coloring scheme will give you a clue of what type of algorithm compiler people have to do. So here's the problem. Here's a sequence of instructions over time, and here's the operands that you're dealing with, A through G. So time is going down this way. So operands tend to have what's called lifetime. They're first loaded and they're operated on and they're stored away, and then you don't have to worry about that operand anymore in this instruction sequence. So what this illustrates is the lifetime of A going from here to here and B going from there to there. So here's the problem that compiler people have to deal with. Is great. They've got all these different operands logically in the program. They have different lifetimes. But what we got to do is find an optimal way to keep them in registers, because let's say in this example we really only have 4 registers you can deal with. So one thing to do is just allocate them into the 4 registers, and then what are you going to do about E, F, and G? You got to somehow cleverly pack them together. The paper quotes an article that somebody said, well, this maps them to something that's called the graph coloring algorithm. That how do you color a graph with only a small number of colors? And there's some good techniques that have been used for that. And the graph coloring algorithm was essentially, let's say instead of 4 registers, there's 4 colors. What we have to do, let's try back like this. What we have to do then is try and mix and match pieces to fill in these lifetimes so we can reuse the registers. So the lifetime, that is, there's no more further references to A after this point, no further references to C. And so one way of doing the graph coloring is to start to move these things around. Here is the E piece. We try and move that one over there. Here is the F piece, and I think we try and move that one in here. And this one we're stuck with. So what we end up is after the coloring under red, black, blue, and green is we have G. We don't have any place for it. So we'd have to what's called spill the registers. That's what we'd have to do, execute loads and stores to find a place to load G. But this is the problem that compiler people face in trying to use registers. This is the reason that in the 70s people said you should raise your eyebrows if you see any registers, because the poor compiler people have to solve this problem. Well, because people kept building machines for a long time that had registers, compiler people came up with a pretty good scheme. The graph coloring scheme that was done at IBM is a really good scheme, and I think that's a variation is what's being done at Stanford, is that graph coloring scheme. Now at Berkeley, we didn't have that luxury of having real good compiler people on our team, so we had to come up with some other solution to this. And our solution, the straightforward solution, was, well, we're going to solve that by having a lot of registers. It's hard to allocate a small number of registers, but it's easy if you have a lot. So if we have a lot and we have more than this 7 or 8 registers, then we can just put them all into registers and not worry about it. So that's what we did. What the problems were, like I said earlier, what about subroutines? Let's see how this is going to work. Okay. So what I want to say is, it seems like a subroutine isn't a very difficult thing to do. Subroutine, you just have to jump to some other location. So what's the big deal? So what I'm going to go through is a sequence to show you why subroutines are really a lot more expensive than a lot of hardware people would have thought, and then show you what we're doing in the RISC CPU in a 2-stage process. So here's brand X CPU. It's got 16 registers, and here's memory location. So it's going to do a subroutine call. Well, what it tends to do is it has its parameters in memory. It wants to use a stack model of passing information, because subroutines can call subroutines, can be recursive, and that's the way to build these systems, and everyone agrees that's a good way to do it. It has the incoming parameters. Because this subroutine, you want to restore it after it's done, you have to save registers away in the save registers area. You need some locals in the subroutine. You allocate those in memory. And then if you're going to pass some parameters for a subroutine call, stick those in the stack. Generally, there's a thing called a frame pointer here that is a register that just points to a particular location, and you can refer to the parameters by saying some positive index or some negative index to refer down here. So that's the way procedures work. Let's do a procedure call and see what happens. What happens is the outgoing parameters of this one or the ingoing parameters of the other. You might modify the registers so you save them all away. You allocate locals and so on. And then when you're all done with this procedure, you have to bring the registers, load them back into memory, and you change your pointer. Now the frame pointer would be down here. Now you change the pointer back, so you'd move it back to this location. Let's try that again. So here's what happens after you've drawn the procedure. Here it happens the other way. Okay, so that's the way subroutines work on traditional machines. A lot of memory traffic involved. I thought you just have to jump and save the return address, but there's a lot more involved in that. Saving a register is allocating passing parameters allocating locals. So what are we going to do in the RISC CPU? Well, one of the things we're going to try and do, the first step of this explanation, is to try and avoid having to save the registers in memory. So the way we're going to do that is having a lot more registers and have a pointer to point at sections of them. Okay, so here's a pointer that points out a section of the registers. So what we're going to do now, we're going to do a procedure call. We still have the parameters and locals and outs in memory. We're just going to change this pointer so you don't have to save the registers away like we did on the left. Okay, change the pointer. We get a new set of registers. We still have this thing going down here in memory of the inputs and locals. And now when we're all done and come back, we don't have to load the registers again. We just change the window pointer. So procedure call, change the pointer, you get a new piece. So you have a lot more registers in the chip, but at any one time you only get a small piece, so that give the programmer the model of 32 registers that he doesn't have to save or restore and procedure call and return. So how could this work? This works because if it's going to work as a buffer. The fact that it has to be the situation that people don't just do random numbers of calls and random numbers of returns, that there's a locality of calls and returns such that this is likely to be a good idea rather than just putting it into memory all the time. So let me try and show you why that might work in this next slide here. Now, what I'm going to do right now is upside down for what's in the, well, let me go ahead and do it the same way it's in the paper. Let's explain it. It kind of depends whether you think calls, whether your stacks go up and down or not. Let's do it like it is as an article in paper. So let's say that the time is going across this way, and time is measured in procedure calls and returns. The number of those goes across this way. And every time you do a call, it goes this way, it goes down. And every time you do a return, it goes up. So let's see what happens here. Now what I've got here is a window, right? Got a window of 4 registers and show you what happens. So the first sequence is call, 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 call. And so this particular program, which is a funny recursive program, is doing, has unusual patterns of calls and returns. So everything's working great. You're at the first one, you do 3 calls, everything's in the buffer. You do one more call, you've filled your buffer up, so you have to make some space. You have to save this one away. So let me go ahead and mark this as an overflow. You slide this down. Oops, there's another call, so you're going to have you have to save this one into memory and move it down again. Another call. Oops, ran out of space. You have to save space again, and you bring it down again. Now, fortunately, now you fit, and so now you do one more call, and you can't quite see this. Let me try and zoom in. Okay, now we're in the register here. So you do one more call, and then another little return, and then a call, and then 2 returns, 2 calls, returns. So we stay in, for a long time here, we stay inside the buffer, and so this is where the buffer is benefiting us. We're avoiding any memory traffic for these 15 or so procedure calls. We keep moving back down, and then we run out of space. We've gone off the graph. We have to save one away, and then it goes down, and we have to save another one away. So we had a couple of underflows there. Then it takes off again, runs into here, saves space, and then once again we should get into an area where we can do calls and returns inside the window, moving across the screen. Okay, so the flavor is then it's a buffer. It's a circular buffer. There's no maximum size to the number of calls and returns, and this style argues it's a locality argument. It's the way people write programs. If people wrote programs where there were 100 calls followed by 100 returns, so they're sharp up and down, this register buffering scheme wouldn't work at all. But in our measurements of C programs, Pascal programs, and Smalltalk programs, we can always find examples where people tend to write these programs. The way people normally write programs is there is a locality of procedure nesting depth that allows this buffer scheme to work. Okay, now that's part A. Now part B is, what wasn't so great about this other scheme is we still had operands in memory. We still had a lot of memory traffic, and it'd be nice if we could bring down the cost of the procedure calls and returns down to 0, close to it. So what we decided was to try and keep these parameters in registers and make these number of registers a little bit bigger. So we've dedicated some of our registers, some of them to be incoming parameters, some of them to be locals, and some to be outgoing parameters. Then what you want to do then is when you want to make a procedure call, you just have to get a new set of registers like this. So we go back and forth by changing that. Now there's a problem here, and what the problem is, we have to, if we do it just like this, we have to copy these parameters, these outgoing parameters, into this location, because the incoming parameters for this guy ought to be the outgoing parameters of that guy. So great, you know, we avoided going to memory traffic, but if we build a machine just like this, what we have to do is copy these parameters into here. So every time we do call return, we have to do like 5 or 6 register-to-register transfers. So that didn't seem like such a good idea. So some students came up with a better idea. So now I'm going to stop and make someone in the audience figure out what that better idea is. So a better way to do this than copying the parameters from this one to that one. We got to get the parameters in this guy's window, but we want to avoid having to actually move the data. Anybody here know what we could do? Nationwide, 415-857-8300. I can wait you guys out. What could you do? All right. See the. Remember what we did before in software routine. What we did before in software is that we would. Okay, I think I'm getting the answer. But remember what we did in software is when everything was in memory, what we would do is we make these parameters be those parameters. How did we do that? Okay, I see there's Morris from. Is this Morris in Bethesda?
Yes.
Okay, Morris, you know what we do?
I would segment the register set one more level.
Okay. What do you mean by that?
Put the local stacks and the parm, well, the local stacks and the in parms and the out parms in 3 separate virtual stacks in the register.
Okay, let's see. So it'd be something like, oh, there are 3 different sets of registers. These are the ins, the locals, and the outs.
Yes.
Like that?
Yes.
Okay. Okay, so then how do we, so we've got a whole bunch of these.
Okay, I'd position them one on top of the other in that register space that you define.
In here?
Yes.
Okay, so this is going to be interesting to do this across the nation, but you'd say this way? Divide this?
Yes. Yes, put the local frame above the ins and outs.
Oh, okay.
Or either way you want to put them.
Okay, like this, you're saying. So
Yes.
local ins and outs, okay?
And have 3 separate window pointers.
Okay, that's an interesting idea. 3 separate window pointers.
Or a pointer that's a number offset.
Uh-huh. And so then you would just, then when you did a procedure call, you would be, you'd be kind of changing these pointers around to get the ins to be the outs of this one?
Yes.
Okay.
And you'd have to manage 3 separate underflow and overflow sets.
That's pretty good, Morris. That's tough to do online. Let me show you what we did, and but that's a good, real close to what we did. Let me show you what we did. What we did was we decided what we do is like the case of the overlapping registers here. Like the case of the opera parameters, what they did is they changed the pointer just to point to here, so they didn't have to move the data. So that's what we did. What we did is when we have these output parameters here, we're going to overlap that with the following frame, so that the only thing you have to do is just change the pointer. So rather than changing the pointer all the way down to here, we just change the pointer to right here, and then that defines the next frame of the window pointer right here, and then we have the next set of locals and then the next set of outs. So because the data is exactly the same, we want these outs to become these ins, so that's what we're doing, see? All right, so by changing this pointer a little bit, the output parameters of the previous guy are the same as the input parameters of the same guy, other guy. That's similar to what's done in software, and that's how we came up with the name called overlapping window registers. So the overlapping between the two registers is a way we can kind of pass the data for free, and that's the full kind of benefit of the idea. All right, now, so here's that was that variation with RISC using these register windows and trying to keep the operands in registers. We find that this is really important to keep these local variables in registers because lots of the references in high-level languages are to that. Here's another view of what I just showed you, is that we have on the order of 128, 130 registers, and they get divided into these pieces, and we just slide this window around this piece. And the register numbers are still registers, just plain old register numbers, register 10 to register 31. So if the programmer's viewpoint is that all the registers are the same, it's always got a 32 register viewpoint, and just the hardware automatically saves things away. Oh, that's great. I can use the screen as a window here. So every time there's a procedure call, the things get slid around, and the hardware automatically guarantees this passing and shifting, and the programmer doesn't have to worry about it. Okay, so what's the difference between these two things? Having the compiler do it and having the register. The disadvantage of the register scheme is lots of chip area, so it could potentially slow the cycle, which is real bad. Another potential disadvantage is you have more registers to store away, on the order of 2 or 3 times as many registers. The only disadvantage of the optimizing compiler is it can make compile time slower, and that it can take multiple passes. And one of the things that they try and do is to avoid having to save and restore registers on calls, is they will inline expand some procedure calls. That is, when they see the call statement, they'll just replace that call by the body of the procedure. When they do this, this precludes separate compilation. So it can be the case, in terms of the hardware designers, it's a lot nicer if you don't use register windows because it's less hardware to build. And maybe from the compiler viewpoint, register windows are nice, and that the compilers don't have to, you can have separate compilation and compilers still be fast. But those are two valid variations on the RISC arguments, and different smart groups come up with different smart solutions. And it'll be hard to say over time which is going to be the best. And in exploratory programming environments that I talk about next, a very important characteristic of exploratory programming environments is how fast you can compile programs. Okay. A second variation had to do, let me skip this one. Go to the third variation that has to do with the pipeline organization. The principal difference between MIPS and the 801 and the Berkeley scheme has to do with the pipeline organization. MIPS actually stands for microprocessor without interlocked pipeline stages. So here's a microprocessor without pipeline interlock stages. Let me show you. Here's a typical pipeline, the RISC-II pipeline. The problem is you don't write the data here until you've already done the execution. So this is writing into register A, and this one needs register A. There's this overlap, because it's pipelined. What we do, and what the 801 does, is automatically forward the data. That is, as soon as the results are calculated, there's some comparator that checks to see if it's the same. If this operand that's being read here is the same as what was being calculated, it passes it along. So here's this forwarding scheme. And that is an attempt to reduce these bubbles that can occur here. Okay? What the MIPS project does is instead, it does that all with software, and the assembler tries to find any conflicts and insert no-ops. And then the second pass goes through and, like I said, inserts the no-ops, and then the third pass tries to exchange the code and tries to eliminate them. For this particular variation, the no interlock detection on blocking, the MIPS guys thought it would make a difference as much as 10% faster cycle. That's what the goal was. But they find, because of the have to inserting of the no-ops that they can't take advantage of, it's about 10% more cycles. So that's kind of a wash. I'd say the designers of RISC-II aren't convinced that it's slows the cycle time very much. And I'd say this is a real interesting thing to try, but I believe the follow-on processes that are being designed at Stanford, the MIPS follow-on project, MIPS-X, is going to go ahead and put that forwarding back in. So for right now, you might try and design a machine without interlocked pipelining, but because the RISC machines are easier machines, they are not as hard to do the forwarding problems. Let me see, I think I got a question from Morris again.
I'm sorry to drop in on your one subject beyond it, Peter.
Oh, that's okay.
What consideration did you give to stacking window pointers and referencing registers via previous window pointers from the called routine?
Okay, that's a good question. Let's see. Here's the problem that was talked about. In terms of, in a compiler model, what's going to happen if you want to refer to that data? So you've done a call and you've got register numbers for these registers. These are like registers 31 all the way down to register 10 here. What are you going to do about if you need to refer to this variable? Particularly in Pascal, you can declare procedures inside of procedures, so you can just refer to something. Now it's in a register. In fact, that's the disadvantage of register-style architectures, is they put operands into these fast locations, but they don't have addresses to them. So there's two solutions to this problem. One solution is just to have a smarter compiler that if you have this so-called up-level addressing, you say, okay, that's got to keep in memory. It's kept in memory. Because most operands are kept, the most likely, the studies that most we've done and others seem to corroborate, is the most likely operands to reference are not these kind of up-level ones, but ones in this frame. Just by keeping it in memory so you can get it at it from loads and stores, that's probably not going to hurt performance much. The other thing that we could do, and we did this in the architecture of the Smalltalk architecture I'll talk about next week, is we put the hardware mechanism in such that loads and stores, you can use loads and stores to get to access this location. That we thought you could do it, so we had built it. It's hard to say that that was worthwhile in performance or in the hardware complexity to put that hardware in so you can get addresses at these locations. Probably an easier thing to do would be to just have the compiler keep that thing in memory like you would in other architectures. Did that get your question, Morris?
Yes, thank you.
Okay. Okay, so that was another variation. Another real interesting thing that they did in the MIPS project was to try and pack more than one instruction per word. Some instructions don't need all of the 32 bits that are possible in a RISC-style instruction format. So they had some instructions that would, short instructions like register-to-register operations or jumps, they'd pack multiple ones per word. And if you could fit 2 per word and you could do it you could maybe run things twice as fast. And they got, again, about another 10% code improvement. The bad news is it was a slower cycle time because it was more complicated decoding. And again, I think this is one that they probably, when they go to the MIPS-X, they're just going to pack 1 instruction per word. The good thing about this variation is the program size. By that metric we showed you earlier, the program size looks good because it can pack instructions in there. The bad thing is it makes the hardware a little bit more complicated to decode. All right, so those are the variations of RISC machines. What I want to talk about right now was what would happen if you try to use some of these traditional RISC ideas on traditional machines. And there have been 2 examples of them, some intentional and some not so intentional. This one is very topical today because Digital Equipment Corporation has just announced this morning a product based on this machine. So let me tell you the history of this. Actually, when I visited DEC in the fall of '79, they had started a project to try and build a Vaxxon VLSI, a fairly formidable task. So that project was presented at ISSCC, an International Solid-State Circuit Conference, in February, I think a year ago, so February of '84. And there were 2 projects that they presented at the same time. One was the full VAX, the full instruction set. It takes 9 chips, 5 of them unique chips and 4 of their copy. 9 chips to build a complete VAX 780, which is pretty great. And then there was another project that I was surprised to hear about, which is a subset VAX. That is, it doesn't have all the instructions. What they found is that 20% of the instructions were responsible for 60% of the microcode, but only counted for 0.2% of the instructions executed. So what this group did was say, hey, let's build a VAX on a single chip, a complete, and all the instructions, this large amount of microcode instructions, let's just trap the software and execute them if we run into any of those opcodes. And that's was a successful experiment. They also have a floating point coprocessor chip they include as well. So what happened? So I think I was told this morning that the VLSI VAX, which is not a product but was mentioned at the ISSCC, was claimed to have a 780 performance no matter how you looked at it. The MicroVax 32 was announced today at having 85% of the performance of a 780 and of integer performance and 80% of floating point performance. So say it's 20% better performance for this one. The number of chips, the difference in the number of chips is a factor of 9 to 2. The amount of microcode is from 480K, that magic half-million figure again, to 64K bits. That's about 1/8 the size. The number of transistors is over 1.2 million transistors compared to 100,000 transistors, so a factor of 10. So in this particular experiment about subsetting architectures, DEC was able to cut the number of resources by a factor of 5 or 10 compared to doing the full implementation. And it looks like to me if the original VAX architecture had been this subset instruction set, gee, that looks like it's hard to see what would have been wrong with that architecture. Another example of traditional machines in RISC is work that was done by DEC on their Modula compiler by Michael Powell, who works in their research group. It's one of the best optimized compilers at DEC. He went to subsetting, a style of subsetting the architecture, and the most interesting subset he did was replacing the call-S instruction. The call-S instruction is a instruction that does everything you'd want in a procedure call. He replaced that by a do-it-yourself, and that one change, not using the call-S instruction with a different strategy of do-it-yourself and using simple instructions, made programs run 20% faster. This is the type of evidence that just warms the cockles of the heart of a computer architect and microcoder. Spend weeks, months trying to get this right, and then by not using that, the compilers can run faster. That just really makes you feel good. Okay, I wanted to save time for questions, so let me go to concluding slides. I think the RISC styles have argued for implementation and architecture to be combined closely together and take advantages of advancements in implementation technology and not worry about having binary compatibility with every machine that was made of this family. Complexity of design can result in a lengthy development cycle such that it makes it peculiar in a highly changing technology. And what's happening with this technology advancing is that you can essentially have mainframe complexity computers in something that is comparable to on a single chip. So mainframe complexity on a single chip. Well, mainframes take a few years in the field to debug, and so I wrote this in the January paper, that RISC have the best chance to avoiding computer recall. This weekend, I came across an article in the San Francisco Examiner by John Dvorak, and it's about digital research. And digital research has a new operating system called, let's see, the title's in here somewhere. But gee, they had a problem. And let me try and not go all the way through it, but the 8286 is a follow-on to the 8086 in addition to the 432, and this has a very highly protected execution model. The good thing about the 8286 is it's also object code compatible with the 8086, which allows it to run a lot of the IBM PC software. Okay. The product is called Concurrent DOS for Disk Operating System 286. Now it seems the problems with DRI, that's digital research, newest product, Concurrent DOS, are plaguing the company. DRI has discovered bugs in the Intel 8286 chip that I assume will force them to change the processor chip in your PC AT or a clone next year if you want the machine to work properly with the newer software. The latest version of the 8286 chip, it's step C2, there's steps in the VLSI designs, contain fatal hardware flaws the DRI discovered too late. The result is a software product that simply doesn't run without crashing. Let me see if I can zoom in to follow as I read. DOS 286 was designed to Intel specification, but when someone went to run it on an AT, it didn't work, although it had worked before on the earlier B1 step chips. Apparently, Intel went to its B2 and subsequent C2 versions of the chip. It added some extensions that threw everything out of kilter. And then here's the problem. It talks about the exception handler. And then it says here, for some unknown reason, the exception handler, the way DRI uses it, manages 95% of the time to trash the 2 register, that CX register pair, where important data are stored and they're referenced by other parts of the computer. And the system goes south for good when it crashes that. This is an uncorrectable silicon problem in the current release of the 8286. Well, there's a quote from Intel in here, too, I want to get to. When confronted with this bug, Intel at first said that it was a documentation error, Erickson said. That's what they always say. They finally admitted the bug and promised a fix. And the fix is going to come in a later step of the chip. Bob Patterson, who's no relation to me, of Intel, told me that no other developers have come upon this acknowledged bug and hinted that it was peculiar to the way DRI designed its operating system as much as anything else. He wanted me to emphasize the 8286 runs fine in protected mode for everyone else. I'm done. Okay. But, okay, so let me come back. And what was interesting about this article, which has happened this weekend, is I hypothesized, it doesn't look like Intel's going to recall chips, but PUR Digital Research is really stuck in the lurch of having a complicated machine that they were relying upon, and particularly their protection model is very complicated. And Intel, and this chip's was presented about 2.5 years ago, and it's been in the field for more than a year, and they've just come across a very sophisticated bug because it's a very sophisticated computer, and it's so built into the hardware, built into the microcode, that DRI, Digital Research, is stuck. If this had been software, clearly software could have been changed to fix the problem, but now poor Digital Research is being suffered with the traditional computing design, and is bearing the consequences of that in a very tough way. Okay, so maybe simpler machines can avoid this problem. I think they certainly can. Let me answer questions now. So I seem to have been longer-winded than I expected. I'm waiting for questions to occur. There's an article about RISC technology moves off the campus in commercial machines in the April 29th version of Electronics Week. And this is John Hennessy. John started a company called MIPSCO. Remember this chip. MIPSCO is a company that's going to try and build board-level MIPS machines. Now, the other person who's in this article is, this person is a Hewlett-Packard employee, and it talks about how HP is going to be coming out. We're broadcasting from Hewlett-Packard. How about HP is going to come up with a family of computers, codenamed Spectrum, that's going to range in performance anywhere from 5 to, I don't know, 15 MIPS on 3 different families of machines. And John Hennessy is promising machines at 2 to 10 MIPS by early next year at the cost of, he said, $3,000 a MIPS, according to this article by Clifford Barney. And so it looks like it says, RISC technology has moved off to the campus and into commercial machines. Here I am giving talks on NTU, and all these guys are, John's going to start a company. Hope has good luck. But how about questions about the ideas as opposed to the commercial? Yes?
The question I have is, do you see the RISC approach being more powerful for different implementations? In other words, if you have like a super mini computer type, will a RISC approach be more powerful there than for like a microprocessor type computer?
Okay. We've actually kind of looked in RISC machines in different technologies. We looked at it in ECL implementation, and in fact, when there were those who were thinking of starting a company at Berkeley, they were looking at trying to do it in ECL. And we, as far as I can tell, everyone who's tried RISC machines, independent of the technology, has had good luck. The characteristics are is it needs to have a fast cycle time, and as long as caches work, you can. Almost every technology I've seen has both a fast RAM and fast logic. And so for ECL 100K or a gate array ECL, they have that characteristic of a fast cycle time and fast logic. The other advantage of this style machine, which has not yet been taken advantage of in a way out technology, what's the first machine you're going to build? You're going to build a 432 or a VAX in gallium arsenide? Certainly not. You want to build the simplest machine you can. So another advantage is going to be with new and way out technologies, people are probably going to build RISC machines because there's less of a gamble of making them work. So as far as I can tell, I'm not aware of either from custom silicon all the way through the well-popular technologies. They've been a very successful effort. A talk was given at Berkeley about research at IBM Yorktown Heights, which is building a packaging technology on 300 pins. And their goal for their cycle time was 12 nanoseconds. So for me, if you can get a 12 nanosecond computer following the RISC ideas in advanced packaging, that's a very fast computer system. Let me answer some more. How about Phil from Burlington? Do you have a question, Phil?
Yes. I have a question concerning how RISC computers work with interpreted languages.
Oh,
I've
that's
got experience with that.
Oh, that's a great question.
Business, and it seems to be a question you haven't addressed.
Great. Fortunately, I get to come back next week. And so let me put in a plug for next week, 11 o'clock Pacific Standard Time, 2 o'clock Eastern Time, next Tuesday, the 21st. I'm going to talk about that, about exploratory programming environments. In particular, I'm going to talk about RISC and Lisp, and Smalltalk, and I'll mention Lisp too. So tune in next week, okay?
Thank you.
How about George from Fort Collins?
Howdy.
Hi.
I was wondering if you had any benchmarks for customers' applications programs, size, main memory size.
What our experience has been that how much bigger programs get, it's about 50% larger. Our experience, going from a compact machine to RISC machine is on the order of 50%. The worst I've ever seen is 100% larger. Because I'm not involved in the company, I don't have any real experience with real applications. So in terms of program size, it's typically 50% larger, and at worst a factor of 2 larger, and that's what you're trading off. Given that memory chips, apparently the 4 megabit chip is what the Japanese are working on now, and they're holding back on the 1 megabit because it'll hurt their sales. I think I'm at least I'd be happy to trade off memory size for performance in my environment, and so that's what we're trying to do. Let me go on to Tim from Corvallis. Tim?
Yes, I'd like to ask a question about hardware support of virtual memory.
Okay.
Earlier you talked about interrupt support.
Okay, let me tell you what I had a student, he's since gone off and taken a job at a startup, but this is what we were doing. We were building with RISC-II a virtual memory scheme that they use in the Sun 2 memory management scheme, which essentially is to have a 2-level page map, a 2-level map of virtual memory out of fast RAMs. So the virtual memory, virtual address goes in here, and the physical address comes out there, and they actually start cycling your physical, the RAS and CAS thing. They do one of them a little bit earlier. So this style of having the complete memory map loaded into these fast RAMs is what's used on the Sun 1 and Sun 2 systems. So they run a 68010 at 10 megahertz, so that's 400 nanoseconds per instruction with 0 wait states. The student at Berkeley said that he thought that we could run a RISC machine at 500 nanoseconds per instruction using the same scheme. So although I didn't talk about any benchmarks, this would allow us to run one program, the compiled program, running compiler about a factor of 2 faster than the VAX 780. And so, although the papers haven't talked about virtual memory, we imagine this kind of scheme would work well with it. And by the way, RISC-II ran at 330 nanoseconds. I didn't mention that, but we had chips that were shrunk and ran fast. So we could, I had a student who has left to join a company, and besides, we're done with RISC-II, we're off to other things. But we think we can have virtual memory as well and still get this high performance. Okay, I think, like I said, I think my time's just about up. Next week I'm going to be talking about Smalltalk and the exploratory programming environments, and if I have time I'll try and talk about recent things that we're doing in terms of floating point performance. We have one more question, or are we all done? tell you what, I'll try and, if there's anybody else on the line, I'll talk to them afterwards. But for now, thanks very much for watching, and see you next week.